Mahalakshmi.
Hello. Yes. என்ன நீ சொல்லுமா சொல்லுங்க. சரி. அப்படியா? Link. Now I'll send the link now. I'll give you that. I'll send it to you now. Okay. Thank you.
Kumar sir, the problem is this Zoom link can accommodate only 100 it seems. I just spoke to the operator. So therefore we have given. I have given you the YouTube link.
Because you said 500, I have given
I said, I thought it is 500. But then now she says, no, it is only 100, sister. Maybe tomorrow I will give you that link, she says, for 500.
Now,
but they can join in.
One of my students is principal in Mayoram Government College. And he is saying that they are not able to join. Most
okay, then I will ask. I will ask them to remove 2 or 3 students of us, so that he can ask him to be ready.
Okay.
I will ask 2 or 3 students to be removed, so that sir can join.
Okay.
Right. Others can join the YouTube link. I have given you the YouTube link.
I will send them the YouTube link.
Okay, sure, sir. Patricia, ஒரு 2-3 பேரை ரிமூவ் பண்ணிரியா? Sir, what is the name of your friend, sir?
Bernice. She is the principal of Mayavaram College. Bernice. Because I have asked to remove some of the students so that
Ma'am can join.
Okay, I'll so today they are.
Once she joins, then we can continue, sir.
Okay.
Yes, sir.
Names. Yes. I have sent it. Papa.
Yeah.
Okay, then has she joined, sister?
She has not yet joined, sir.
Oh, okay. Thank you, sir. Because I said tomorrow they may increase it. She said,
yeah. Tomorrow it will be 500, sir. Tomorrow
so
500.
that message she has said, thank you.
I think they forgot to recharge, it seems, sir. Recharge. In the call, this is a college ID. Using the college ID only, we are creating this link. So I think they have forgotten to recharge. So only 100 can be accommodated.
Okay.
Yeah, tomorrow will be 500.
I never thought it will exceed 100. But because you said 500, I gave it to my students. They are all positions now, like HOD, principals.
Anyway, let them join by YouTube link, sir, today. And maybe we'll...
the YouTube link is there, huh?
Yes. Side by side, the YouTube link will be there.
Right. Then
yes, I have sent it to you, sir.
Okay, you have sent it. They can join. Happy voter. They can join. Oh, I'm also learning so many things. Today itself. There will be some delay. Right,
so that is why our technical assistant ma'am said that she is removing a few students so that principal can join.
I don't know whether she will join. Maybe her students will join.
Anyway, they can join
it in your name. That's why I said join. They can join.
So if you are ready, we can start, sir.
Yes, sir. We will start.
Okay, sir. Madhumita?
Yes, sister.
Yes, ma'am.
A rainbow is the product of physics, working for your appreciation of beauty. When you start to explore physics, it becomes the most beautiful part of your life. A very warm welcome to one and all gathered here for this webinar on microprocessor and microcontroller for college students. One song can change a moment. One idea can change a world. One step can start a journey. But a prayer can change even the impossible. May I now request Dr. Reverend Sister Jessie Fernando, HOD, Department of Physics, to begin this webinar with a soulful prayer.
Dear friends, at this juncture, let each one of us raise our heart and mind to thank and praise God Almighty for His abiding presence, care, and enlightenment that we have experienced all through this year. Let us remember with gratitude all those who have extended their wholehearted cooperation and encouragement towards the realization of many things for the past 12 months. And now, in a very special way, let us pray to God from the depth of our hearts to bless today's resource person, Dr. Kumar Satyan, who has joyously consented to share his knowledge and experience regarding microprocessor and microcontroller. May God Almighty shower His abundant grace and blessings upon Sir these 2 days with good health, mind and soul to inspire and motivate our students across the country to develop a keen interest and unflinching desire to explore new avenues in life. Thank you, Lord, for this wonderful opportunity, and we all of us seek your blessings to participate well in these moments of learning. Bless all those who are helping us in many ways to realize this lecture. We make this prayer in the name of the Heavenly Father, Son, and the Holy Spirit. Amen.
Amen. Thank you.
Joy waits on welcome, not time. Small cheer and great welcome makes a merry feast. May I now invite Dr. Reverend Sister Jessie Fernando, HOD, Department of Physics, to welcome the resource person and everyone connected.
I deem it a great honor to welcome all of you connected with us in this program. First and foremost, I thank God Almighty for this wonderful hour of learning. Now, I'm indeed very happy to welcome our dear resource person of the day, Dr. G. Kumar Satyan, former academic dean and head and professor of physics at Madras Christian College, Tambaram, and at present the managing director of Floronics, a manufacturing company of educational electronic trainer kits, who is going to speak to us on an interesting topic, 8085 microprocessor, addressing modes and programming techniques. Amidst this busy schedule, Sir has consented to deliver this lecture for the benefit of the students across the country. Sir, I extend a very, very warm welcome to you on behalf of our college management and the Department of Physics, and I take pleasure in welcoming also our Reverend Sister Secretary, Reverend Sister Principal, the overall coordinator of the STAR program, Dr. Sister Aroke Alphonse Genetius, and all other respected members of the academic and administrative team, and the members of the Marian Star Center, and the technical team of our college assisting us in this program. A very hearty welcome to all my dear students who are actively going to participate in this program. Now I would like to introduce the speaker, Dr. G. Kumar Satyan, who has served as the head of the Department of Physics, academic dean, and one of the directors of Madras Christian College Board, and retired in 2008 after serving 38 years at Madras Christian College, Tambaram, Chennai. He has served as a guest faculty in the Department of Theoretical Physics, University of Madras, for 3 years, and also as a course coordinator since 2011 for the UGC-sponsored add-on course, Learning Electronics through Mini Projects at JBAS College for Women, Chennai. At present, he is the managing director of Floronics Company, founded by his experience and passion in electronics in 1986. The firm manufactures educational electronic trainers for use in electronic labs of engineering colleges, arts and science colleges, and physics labs in schools for the past 3 decades. All the educational trainer kits required for setting up digital, operation amplifier, microprocessor, and microcontroller labs were designed and developed by Dr. Kumar Satyan at Floronics. His research experience too is very deep. He has worked on solid electrolytes, solid-state batteries in the field of solid ionics for his PhD from the Department of Energy, University of Madras, and he has 6 research papers to his credit. He has guided more than 100 MPhil students and more than 300 MSc and BE projects based on microprocessor and microcontrollers. Recently, he has developed interest in designing and guiding student projects based on embedded microcontroller ATmega 328, and he has developed a motherboard Flordiano based on ATmega 328 and paved the way for doing many sensor-based electronic automation instrumentation projects to be undertaken by UG as well as PG physics students. Recently, sir has designed and developed do-it-yourself embedded systems projects for school children, highlighting the concepts of sensor-based electronic automation for robotics and IoT applications, kindling their quest for experimental knowledge with hands-on experience and their passion for electronics. He has published lab manuals for digital, analog, microprocessor, and microcontroller experiments for electronic students. Sir has given his expertise by being a member in many academic and consulting bodies, and he has served as chairman in the PG Board of Examiners for Madras University and MS University, Tirunelveli. He has been a Board of Studies member in the University of Madras and several autonomous colleges in Chennai and in Tamil Nadu. Now he continues to serve as a Board of Studies member in more than 15 colleges as an industrial expert and shares his 40 years of expertise with the academic community. He has served as a coordinator and as a resource person in many seminars and lab-based workshops in several colleges and at the Birla Planetarium, Tamil Nadu, Science and Technology Center, and in Academic Staff College, University of Madras. He conducts regular internship courses for BES, BE, and MSc students in his company, Floronics, during summer holidays. His aim is to make electronics easy and interesting for learners and share his abundant knowledge gained through his experience with students and staff and serve the community as long as God permits. Sir, we are indeed very fortunate to have you amidst us to share your learning resource with us. Once again, I welcome you, sir, on behalf of everyone connected here. Thank you, sir.
Thank you, sister.
To attain knowledge, add things every day. To attain wisdom, remove things every day. Nothing in life is to be feared. It is only to be understood. Now, it is time to understand more so that we may fear less. I now hand over the session to Dr. G. Kumar Satyan. We are waiting to understand and gain knowledge from you, sir.
Thank you. So shall I start? Yes.
Yes, sir, you can start, sir.
Okay. So thank you and good afternoon to everyone. At the outset, I thank Reverend Secretary and the Principal, Sister Rose, and the Head of the Department, Sister Jessie, for having given me this opportunity to deliver 2 lectures from my passionate subject, electronics, as a resource person for this national seminar. It gives me a lot of satisfaction to share my knowledge and experience I gained at MCC when I was serving as a faculty there. Also, I would like to thank Dr. Padmavati, Assistant Professor of Physics, for having initiated all the preliminary steps in entering into an MOU with my company, Floronics at Chennai. I thank the coordinators of this seminar and all the colleagues of the department who associated themselves with preparations for this seminar. I thank the students of St. Mary's College, Tuticorin, and especially my ex-students at MCC who have encouraged their students to register for this webinar A warm welcome to all of you. I wish to see you in person, but this pandemic threat has kept us apart at a distance. Thanks to the present technology, the internet has, however, connected all of us together in this webinar. Thanks be to God. Now let us have a word of prayer from my side. Sister has prayed very well, but anyhow, I attribute first few minutes to the Lord in prayer. Almighty and loving God, we praise and thank you for gathering many inquisitive minds who have logged into the net to upgrade their knowledge. Lord, you are the source of all wisdom. Be with us and bless the entire proceedings of the webinar arranged by St. Mary's College, Tutugarin, under the Star College status. Lord, enable my lectures to be useful to all the participants. Let them get a clear picture of the emerging technology and the awaiting socio-economic problems of the society, and come up with innovative proposals to solve the age-old problems with new age solutions. Let India become self-sufficient in all aspects with better standard of living and dwell in peace and harmony granted to us by your love you have for the mankind. We ask these in thy precious name. Amen. Now I wish to say a few words before I start. See, Tutugarin is famous for two things. One, harvesting pearls, and two, producing salt. St. Mary's College has excelled in both things. It's my observation. In gathering many inquisitive minds, the pearls of Tutugarin for this webinar. Two, salt adds flavor and taste to our delicious food. That way, St. Mary's College has planned to add knowledge and exposure to sync with the data explosion. Now, let me go to the presentation. Yes. Today's lecture is going to focus on 8085 microprocessor architecture, programming, and interfacing techniques. I wish to refresh our memories. Way back in the 19th century, Boolean, a mathematician, proposed that there are three fundamental logic operations, namely AND, OR, and NOT. Later, NAND, NOR, and XOR functions were proposed. NAND and NOR gates became universal gates, as all the logic functions can be derived from one of these gates. While these gates perform logic functions, XOR performed arithmetic functions like addition and subtraction. Thus, all decision-making logic operations and the arithmetic operations can be performed using the logic gate NAND or NOR. This gave birth to digital electronics. Digital circuits replaced electronic circuits, providing reliability and high resolution. With the introduction of integrated circuits and microelectronic fabrications like SSI, LSI, and VLSI, we had programmable hardware circuits like microprocessor. So microprocessor is an hardware, but it can be programmed. These microprocessors are basically digital circuits dealing with binary numbers 0 and 1. They have the capacity to store the data and the coded instructions in its memory registers. These instructions can be executed one by one sequentially to perform one of many solutions. Since the digital machines can understand only binary digits, zeros and ones, they call it as machine language. One has to code the instructions to be performed in binary logic, binary coding, and arrange them in the required sequence to obtain the right solution. This language is called assembly language, using mnemonics, abbreviated English words. This leads us to microprocessor programming. Let us study the different techniques involved today. So you see a short introduction about 8085, and now you see we go into the depth. 8085 microprocessor is a 40-pin LSI chip. I told you SSI, LSI, and VLSI. In a small area, 4 mil by 4 mil thickness, integrated electronic circuitry, the design has helped us to have this 8085 microprocessor, 10,000 transistors inside. A 4 millimeter by 4 mil by 4 mil. 1 mil is 1,000th of an inch. So that is this complexity of circuits present inside the chip, which is 40 pin. 8085 microprocessor is an 8-bit digital processor. It handles binary data 0 and 1. It has an 8-bit data bus for handling data and instructions. Data ranging from 00H to FFH. That's the maximum at a time we can have. 00H is a X code. FFH is also a X code. Its digital equivalent is 0 to 255. FF stands for 255 decimal number. So your data you can handle from 0 to 255 in decimal or hex 00H to FFH. And also there are 256 instructions. They are all coded in X form from 00H to FFH. The reason being the data bus is only 8-bit. So 2 to the power of 8, we have 256 instructions. So the data and the instructions are both stored in memory before we start the execution. That is the one thing that we must know. That is the type of architecture which we are using in 8085. The size of each data is 8-bit wide and is called as a byte. Now, for those people who are not familiar with X codes, I have prepared this slide. X code consists of 4 binary bits. What are they? B0, B1, B2, B3. 4 binary bits grouped together forms one X code. In decimal, we have 0 to 9 digits. But for hex code, we have 16 digits. We have selected 16. This is called alphanumeric code. All the alphabets 0 to 9 are used for the 10 digits, first 10 digits, and English alphabet A, B, C, D, and E, F. These extra 6 English alphabets are also joined So totally we have 16 X digits using 4 binary bits. For example, to put 0 in hex form, X code, you will have to put 4 bits of zeros. 0, 0, 0, 0. So these are the 4 binary bits put together form one X code, and which is equivalent to in decimal 0. If the decimal number is 1, then we have the binary bit. LSB bit becomes 1. The remaining bits are 0. Weighted addition. Final binary bit 1 to power 0 is 1. This is binary bit 2 power 1. If there is a 1 there, the weightage for a 1 in this bit is going to be 2. Similarly, the weightage here will be 4 and the weightage here will be 8 if there is a 1 present. So it is called 8421 code. So to present a 1 in decimal X code, we have to put 4 bits 0001 and that represents 1. Similarly, we say 0010. See here, it is 2 plus 0, so its value is 2. It is X form. So X code and decimal numbers are going to be the same till we come up to 9. You see that 9 is 1001. Weightage of 1 here is 8. The weightage of 1 here is 1. So add together, you get 9. So up to this, the decimal number system and the X code are the same. But when we come to 10, the binary representation is 1010. See that? The binary is correct. 8 is the value of this one. 2 is the value of this one. So add together, you get 10. But we cannot write 10 in one digit, single digit. So we have incorporated alphabets. So A is equivalent to 1010. This is what you should remember. So when you come to microprocessor, you think you are coding in X code. It is very much similar to binary codes, which a machine can easily understand. So the machine language is only coding the instructions or the data in X code. Similarly, you see this is 1 plus 2, 3 plus 8, 11. 11 in decimal number, binary number will be 1011. In hexam code, it is B. So 3 codes we know. Decimal codes we are very much used to. Binary codes deals only with zeros and ones. And the group of 4 binary bits give rise to a hex code. So C is equivalent to decimal number 12. And in binary representation, it is 8 plus 4, 12. Similarly, we have D 1101 and E 1110 and F. All the digits are 1. Then what we get, it is 1 plus 2 plus 4 plus 8. It comes to 15. So the maximum single digit X code is F and its decimal equivalent is 15. So this is how we have to understand X code. 8085 can handle 8 binary data bits. That means it can handle 2 sets of X codes. D0, D1, D2, D3, the what you call this nibble, lower nibble forms one X code, and the upper nibble, D4, D5, D6, D7 forms the second X code. So you have got 2 X codes, D0, D1, D2, D3, one group, D4, D5, D6, D7, second group. And the X data will now vary from 00H to FFH for the 8 bits of binary data. So the X code is now can be easily written instead of writing 4 plus 4, 8 bit binary bits. If you say 00H, yes, you have to imagine that this 0 corresponds to 4 binary bits 0. Similarly, this 0 here corresponds to 4 binary. So 00H corresponds to 8 zeros. See here, 0, 0, 0, 0, 0, 0, 0, 0. D0 to D7, 8 binary bit. If the take this value 000, then the X code will be 00H, and the decimal equivalent is going to be 0. We are always correlated with the decimal number because we finally take all the decisions in decimal representation only. But the machine can understand binary language, and coding is done in X code. So you must be familiar with the binary code, the X code, and the decimal code. See here, I have put all of them are 1. D0 to D7, all the bits are 1, which is X representation in FF. In decimal equivalent, you add, this is 1 plus 2 plus 4 plus 8 plus 16 plus 32, double it, 64 and 128. If you add all of them together, you get a decimal value 255. For example, to just explain, if you want to put X number 01, then the decimal binary number D0 will only become 1 and the decimal value is 1. Here, if I put MSB bit as 1, the remaining things are 0. The first 4 bits, 1, 2, 3, 4, they form the X code, which give rise to 8. And the remaining 4 binary bits grouped together give rise to the second binary X code, which is 0. So it is 80. And because 1 is existing under the MSB bit, the value of the decimal bit equivalent will be 128. Similarly, here I have put 0000 and 1111. The upper nibble is 0. So the X code for that is 0. And the lower nibble is F1111. So the second X code is 0F. The equivalent of the decimal equivalent is 15. Similarly, 111100 will be F0 and the decimal equivalent will be 240. So next, we have now gone through the X code, how we can represent a decimal number into binary number and group them in 4 and get the X codes. So a data bus transports, this is very important, you must keep it in mind, transports 2 things, data, 8-bit data, or instruction opcode. We have to have the data and the instructions opcode stored in memory before we start the execution of the program. So this data transfer takes place between registers inside the CPU through internal data bus. So you see, the 8-bit data are transported from register A to register B or register C, whatever it is. There are so many registers, 7 registers, general purpose registers are there. You can transfer contents of one register to another. So that's what we say here, transfer of data between registers from one register to another. Yes, it is possible. It is done through internal data bus. What is a bus? Bus is a group of lines, a set of lines. In this case, you are handling 8-bit data, therefore it is a 8-bit bus. So 8085 has 8-bit data bus, internal data bus is 8. Or the data can be transferred from the registers or in the register, can be transferred from the registers to memory. See, memory device is also 8-bit register. You can transfer the data from memory to the registers in the CPU. So CPU has got 7 general purpose registers, all are 8-bit registers. You can transfer the data from any one of the registers in the CPU to memory. Memory is sitting outside. So you can have transfer. So this is also done by a data bus. If you want to transfer 8 bits of data from a register in CPU to a memory register, which is also 8-bit register, yes, you can do it only through a data bus, but we call it as an external data bus. So data register, transfer of data between registers inside the CPU is done through internal data bus, whereas the transfer of data between the registers in the CPU and the memory is done through external data bus. Similarly, I/O device, input and output device, keyboard gives you a 8-bit data input, which can be taken to any register, that is accumulator register in the CPU. Similarly, whatever be the content of the accumulator register can be output as LED display. So that is the output device. So you have got input and output devices. They register. They also have buffer registers, or we call them as port, and they will have their data stored before sending it to the accumulator, or from the accumulator, they will receive the information. So this is how the 8-bit data can be transported via internal data bus and external data bus. There are 16-bit address bus. 16 address lines forming a 16-bit address bus. Why 16 address lines, you may ask? You see, in the CPU, I told you, there are only 7 general purpose registers. That means you can store this 8-bit data in a register. Only 7 8-bit data can be stored inside the CPU. That limits you to have only 7 data. But if you want to have more data, suppose you want 16 data, then you are out of registers. So people thought of having memory registers in different devices, so like RAM and ROM. So the RAM and ROM are memory devices, but they are nothing but 8-bit registers each. So like that, memory registers are, the size of the memory register is 8-bit, but how many of them you can have? And the Intel company who manufactured 8085 decided on 64,000 bytes of words. It's 64,000 8 bits. So 64K. 1K in digital represents 1024. 2 to the power of 10 is 1024. So that way, we are having 64,000 bytes of data, 8 bits data. For handling, we must be able to select one of the data. We must be able to select one memory data, read it or write it. So for that, we must have decoder circuits. So the decoder circuits need input information. If you have 16 address lines going into the decoder circuit, 2 power 16 minus 1 outputs can be decoded. So in this case, 2 to the power of 16 minus 1. So if you have 2 power 16 address lines, then you will be able to select 1 of 64K memory. So 1 of 64K, how do we get it? 2 power 16 can be separated as 6 plus 10. 2 power 6 comes as 64. 2 power 10 comes as K. So you have 64K memory locations. So we need 16 address lines to select 1 of 64K memory locations. Then 16-bit address or 16-bit data are stored as bytes. Say all are 8-bit registers. How are we going to store a 16-bit address or a 16-bit data in 8085? Yes, this is also possible. In memory, they are stored in 2 successive memory locations. They are stored in 2 successive memory locations. Say a number 1234H, which is data. 1234H is a 16-bit data. This can be stored in 2 memory locations, 8050H and 8051H. The lower nibble, the lower 8 bits will be stored in first memory location, and the upper nibble, which is the higher order hex code, will be stored in the next memory location 8051. So this is the practice. 8050, the first memory location, stores the lower. So 34 is in 80508, and the upper hex code, upper nibble will be stored in 8051. So this is how we are able to store, and there are 16-bit registers. Some of the registers say PC, SP, and these are, they can store the addresses. So directly, therefore, they are 16-bit registers. In addition, the registers A is a register, A is a 8-bit register, but B and C can be grouped to hold a 16-bit data. Similarly, D and E can be grouped. Both are 8-bit registers. They can be grouped to hold a 16-bit data. And H and L, 8-bit registers, can be grouped to hold a 16-bit data. So this is how we can solve that problem. Then there is one extra thing the Intel company has done. What they have done is they have multiplexed the lower byte address bus A0 to A7 with a data bus D0 to D7. See that lower byte address bus A0 to A7 and the data bus, 8-bit data bus D0, D7 are multiplexed. So same address line will send the lower byte address and also hold the get the read. When you read, you are getting the data D0 D7 will come in the same line. So the lower 8 bits will be sharing address and data bus. So we name them as AD0 to AD7. The first 8 lines out of the 16 address lines, A0 to A15, you have A0 to A7 and is shared with D0 to D7, and it is referred as AD7 to AD0. But you see the data is two-way communication. You may read the data, that means it is going into the CPU. You may write into the memory, it is going out. So that this AD0 to AD7 has read and write data, so it is bidirectional. So that 8 bits are bidirectional. Whereas the higher order address lines, A8 to A15 is single direction, unidirectional. So it is only going to output address, higher order address. So it is unidirectional bus. This arrangement of multiplexing the lower address line with data lines, you save 8 pins. Instead of saying A0 to A15, 16 address lines separately for address bus, and D0 to D7, 8 data lines for data bus, you will have to spend 16 plus 8, 24 pins. We are limited with 40 pins in the chip, and it has to have a lot of work to do. So what they have done, they have multiplexed it and saved 8. They are not. They will occur at different instant of time. When you give the address, you are not going to read. So give the address at one instant of time, and after different clock cycle, you read the data or you write the data. So that way the data will go after different clock cycle time, and say there will be no confusion for the processor, and we will be able to save 8 pins. That is called multiplexing. This arrangement saves 8 pins, and it is used differently, efficiently for producing interrupt pins. We have interrupt pins, serial in and serial output pins. They are all special purpose pins, operations, which can enhance the quality of working of the microprocessor. So the Intel company has achieved in introducing special efficient operations by multiplexing the lower order address bus with data bus. So this is the bus structure. 8085 microprocessor is here. A0 to A15. Now we have put it as separate, only for this understanding. You make it easier. A0 to A15 forms the address bus. You see the address bus, 15 bits address bus, go into the decoder section of memory. So the decoder section receives the 15 address lines, A0 to A15, and selects one data, one memory selected. The content of the memory is only 8-bit. So the 8-bit data is either presented here. So it comes as output. So here when this arrow says it can come out to data bus. So provide the address to the memory A0 to A15, and after some time the decoder circuit presents a 8-bit data to the data bus. Then you can read. So when the read cycle comes in, you will read the data D0 to D7. So it comes through the data bus. At the same time, you see the address bus goes. It can be 16-bit address or 8-bit address that goes to the input and the output line devices. Input and output devices have their own separate decoder, and these 8-bit address or 16-bit address goes to input decoders or the output device decoders. So they select one of 64K or one of 256 input devices. If it is 8-bit, 2 power 8 is 256. So it selects one of 256 input devices, and from there, whatever the address, it takes the, here it is input, it outputs the data. So the device gives the information, and that is read to the microprocessor. This is input data. Similarly, whatever data you have, you can either write it to the memory or you can write it to the output. So from the accumulator, it goes through the data bus and it goes to the output device, the address is selected here, and it goes to the output. Similarly, see, you have got address bus and data bus. They are controlled because they should not have any confusion. So there are control bus, RD bar, WR bar, and IO memory bar. The IO memory bar line is one of the control lines, which if it is high, it will enable only the IO devices. If IO memory bar line is low, that single line does two operations. It either enables the IO devices or the memory devices. Memory devices are here, the IO devices are here. So if the control bus IO memory bar line is high, it enables the output decoders. Similarly, if it is 0, then IO memory bar is low, therefore it will enable the memory devices. After that, so you have got two devices, we have separated, either it is input or output. Then comes, once that is there, memory or IO. Memory or IO we have separated. We do reading or writing operation. So when you say read bus, the control bus gives reading operation. So the address is given and you read the data and the data comes to the data bus. So this is a reading operation. In this time, RD bar goes slow. So IO memory bar line goes slow. And if RD bar line is also going low, then you will be doing the reading operation. If IO memory bar line is high and you do the reading operation, that is RD bar goes low, IO is high, so it enables only output devices. So that way you are reading the output, reading the input devices. So that way, then WR bar for writing operations. So the control bus is connected to memory and input-output decoders. So this is the bus structure in 8085. And this is the overall architecture, internal architecture. You can see there are some general purpose registers. A is the accumulator and B, C, D, E, HL. So these are the accumulator register is here, and you have 2, 4, 6. These are the 7 general purpose registers, B, C2, D, E, and HL. 6 single 8-bit registers are available, and in addition, we have temporary registers, WZ, 16-bit register, which is not accessible to the user. So general purpose registers A, B, C, D, E, H, L. These are the 8 registers which are accessible for the user, and we can now group these 2 registers B, C as 16-bit, and we can call it as a B register pair. Similarly, we can group D, E and call it as a D register pair, and HL can be combined together to give H register pair. Therefore, in addition, we have stack pointer. We'll be pointing to the top of the stack. You have a stack area in the RAM, and that will be always pointing to the top of the stack. Program counter points the instruction to be fetched next. So instructions are sequentially stored in memory, and the program counter provides the necessary address, and it will place it in the memory address register buffer, and that will go to the memory section. So this is how the internal architecture. And then you have got ALU, accumulator, temporal registers, flag registers, all these things put together. You get this ALU, and they perform arithmetic logic operations. 8085 register. So this is what I was explaining. It is accumulator is a 8-bit register, flag is also a 8-bit register. These two form a 16-bit register, and it is called as program status PSW. PSW is a 16-bit register. The most significant byte is accumulator. The least significant register is flag register. And BC can be combined as B, DE can be combined as D, HL can be combined as H. So these are the registers available inside 8085. Then I told you, this is what I have explained. 6 general purpose registers, an 8-bit accumulator, and a flag register. Each register has got a code, 3-bit code. They have allotted a 3-bit code for each register. A is given a code 111, 3-bit code. B is given the code 000, and C 001, D 010, E 011, H 100, L 101. So with this, we will be able to form opcodes. Say we can name the register with this code. Okay, so this is how 3-bit registers are. The register is given a 3-bit code. B, C, D, H, L register can be used as 3 16-bit register pairs, D, B, C, D, and HL pairs. Now you see, these 16-bit registers can store 16-bit address or 16-bit data. They can be used as memory pointers. If it stores a memory address, 16-bit address, then it will be in the CPU. The registers are in the CPU. But if the data is in the CPU, it refers to a memory address. So even the 16-bit registers hold a data which is referring to a memory register, then they are called as memory pointers. So you can use HL as a memory pointer. If HL has 8050, 80 in the higher order byte and 50 in the lower order byte, 8050 that is the 16-bit data. Now you can say that 8050 is the memory address. Yes, that way HL register points to 8050 memory location. It acts like a memory pointer. When this HL register acts as a memory pointer, then it is referred as M. This is a small thing that we should remember. BC can store 8060. DE can store 8070. When BC stores 8060, we can say it refers to a memory location 8060. In that case, BC is also a memory pointer. Similarly, DE stores 8070. That means DE is pointing to memory location 8070. But if H stores 8050, it points to memory location 8050H. And for it is called a memory pointer. And at the same time, it is referred M. HL register is not referred as H when it points to memory location. Whereas here, BC register pair will be referred as B register pair, D will be referred as D register pair, but HL register pair, when it be pointing to memory, it acts as a memory pointer, then it is referred by a letter M. Excuse me. Program counter, PC, is a 16-bit register used to store the address of the instruction to be fetched next. It keeps track of the sequential flow of the program. We need not be incrementing the memory locations, so it is done automatically. And that is taken care of by the program counter. After the execution of every instruction, the program counter will be automatically incremented so that it can fetch the instruction from the next memory location. Then you have stack pointer. Stack pointer is referred as SP. It is also a 16-bit register. It points to the top of stack. Stack is a part of RAM used to store 16-bit data temporarily from a 16-bit register during push and pop operations. See, this is a very powerful instruction. If you want to store a 16-bit register, you can say push B. That means the content of B and C, which is 16-bit data. So every push operation will push 16 bits of data. For a single operation, it will push 16 bits of data. So they are pushed to two successive memory locations in the stack, that is in the RAM area. A portion of the area is used for stack, and the stack pointer points to the memory location, the top of the memory location, and using push and pop operations, we will be able to store, push the 16-bit content of registers BC, DE, and HL, and program status word PSW into the stack temporarily. When you say pop, the data will be taken from the stack to the respective register pairs. If you say pop B, the topmost two memory locations will be popped to B and C. The first data will be taken to C, and higher order data, that is the second memory location data, will go to the higher order register B. So this is how push and pop operations happen. Also, stack stores the return addresses of subroutines from the PC program counter automatically. You have instructions for branching. That way you can jump or you may call back. You can call subroutine. When you call a subroutine, you are supposed to come back. When you jump, you just jump. You don't come back to the main program. But if you use call instruction, you have an intention to go out of the program area, perform the instructions in a new area. After the end, you come back, return to the main program. So the return address, that sequence has to be maintained. That will be automatically stack whenever you use call and whenever the return instructions, it comes back, the program counter is loaded with the return address from the stack. So this is the role of stack. WZ is not accessible to the user. It is a 16-bit register. Then why, sir? It stores the addresses temporarily during the execution of branching instructions such as jump, call, interrupt. So these WZ instructions can be used for checking whether the condition is satisfied or not. Some temporary registers are necessary, and therefore we are having a provision, WZ register, the data will be, if the condition is satisfied, you branch out, otherwise not. So you have got jump and call instructions and interrupt instructions. They have subroutine inside, micro instructions are written inside to check J and C, jump no carry. J and Z, jump not zero. Jump JC, jump carry. So that way we can give conditional call instructions and conditional jump instruction. During which time, if the condition is satisfied, then otherwise you fall through. For that, there has to be a temporary register which can be used for the comparison. One minute, let me. Then comes 8-bit ALU. It does all the arithmetic and logic operations. It aids branching instructions by affecting the appropriate flag in the flag register. So after the execution of any arithmetic or logic operation, there are 5 flags in 8085. They are accordingly altered. The status of the flags are altered. If the content of register becomes 0, the Z flag becomes 1. If the carry flag, there is a carry taking place from the MSB bit, then your carry flag will be set. If there is a carry between the bit A3 to A4, there is a carry. First nibble to second nibble, there is a carry. Then auxiliary carry flag will be set. If it is a negative number, the sign flag will be set, or then you have the parity flag, odd parity, even parity, you have parity flag. So like that, the 5 flags are, the status of these 5 flags are affected depending on the arithmetic and logic operations performed in ALU. So the ALU does that also. It performs only 2 operations. 8085 performs only 2 operations. So we can now reduce the entire discussion to only 4 things. You see, it performs 2 operations with 2 devices. That's all. 2 devices, memory device and IO device. It does 2 operations, either read or write operation. You may read from memory or write into memory. You can read from an input device or write into an output device. So there are only 2 operations performed, read or write, and on 2 devices, memory devices and IO devices, giving rise to 4 basic operations. The basic operations are memory read. In short, we call it as mem read bar. I put a apostrophe here. I cannot put a line here. So mem r bar, MEM, mem read bar. So mem r bar and memory write, mem w bar, and IO read, IO r bar, IO write, IO w bar. I told you RD bar, WR bar are active low. So when memory read comes, the IO memory line will be low and the RD bar line will be low. When both of them are combined, you get mem R bar line, which is going low. So this is active low, which will initiate the memory read operation. The memory devices will be enabled and the read operation will be performed. Similarly, if you say IO read operation, that is memory IO read, IO memory bar line will become high. At the same time, you are doing reading operation. So IO R bar, RD bar will go low. That way, IO R bar line will go low and initiating the input device to input the data. Similarly, we have memory read and memory write and IO write, supported by active low control lines, which I have written here. ALE latches the address. IO memory line, it differentiates between memory devices and IO devices. RD bar and WR bar lines differentiate between the reading and writing operations, along with status lines S0 and S1. So these 5 lines constitute the control bus. So we have got 3 buses in 8085, data bus for handling data, address bus for sending the 16 address lines to select one of 64K memory devices, and then we have got control bus consisting of 1, 2, 3, 4, 5, 6 lines which form the control bus. So this is the table of column which I have put to make it very easy for you to understand. Memory read operation. This is meant for BSc students. MSc, please ignore this, or you please adjust to that. So memory read, mem read bar. I have not put bar here. Memory write and IOR bar, IOWR bar. So W bar. See, in this case, IO memory bar line will be 0 because memory line is memory devices are initiated for memory read operation. RD bar line goes low so that you can do reading operation. These two are exclusively opposite. RD bar is low, WR bar has to be 1. If the WR bar is 0, the RD bar has to be 1. So these two are exclusively opposite. And I think I have explained all this. So we can pass to the next slide. 0 logic status at the control signal. IO memory bar activates the corresponding memory operation or the output operation. Logic 1 logic status at the control signal activates the corresponding IO operation. Now we have come to the set of instructions. There are 3 types of instructions. 8085 has 3 types of instruction. 1, single byte instruction, double byte instruction, and 3 byte instructions, depending on the operand size. It is 3:45.
Sir, no problem, sir. You can continue, sir.
Because we started now.
Yeah, no problem, sir. You can continue, sir.
Pick up another half an hour. Okay.
Sure, sir. Sure, sir. No problem, sir.
I have about 60.
It is quite interesting, sir.
Oh, thank you. Thank you.
Yes, sir.
There are 18 mnemonics. 18 mnemonics means the abbreviated words I told you. MOVE, M-O-V-E is the actual spelling. But we write only M-O-V. And we understand it is move. Like that, load accumulator directly. We may write long, lengthy words. Instead, we say LDA. Store accumulator in the memory location. STA. So that way we use mnemonics and represent the operations. For our sake, it will be easy. And there are 80 mnemonic. But you have 2 to 6 instructions. Why? There are 8 data bits. So 2 power 8 is 2 to 6 instructions are possible. They are coded from 00H to FFH. So that way, using 80 mnemonic, we have to generate 2 to 6 instructions, and they are all available in the instruction set. You need not have to worry about all that. Slowly, we will learn the mnemonics as we go to the program writing section. Okay, so 18, keep it in mind. We are not going to use all the 18 mnemonics. We may use over 10 or 12. That's enough. With that, we will consider use about 100 instructions, or and we will be able to write programs. Opcodes in X for instructions. See, we are generating the opcode for instructions move A, B and move B, A. You may be familiar with this type of instruction. It is a data transfer instruction between registers. You are saying that the content of B register is moved to A. Move A, B. This A stands for the destination register, and this B here represents the source register. So you say the source register is B, so the content of B is transferred to the destination register A. So move A, B, and move B, A, it is the opposite of that. The content of A is transferred to B register. What happens? That's important. So you see that B is transferred to A, here A is transferred to B. For us, it's okay. But for a machine to understand, we have to use the opcodes. We have to generate. You see the opcode move, then it has got 3 fields: opcode, destination register, and source register. In this case, move is the opcode. A is the destination register and B is the source register. So we know previously I said B register has got a 3-bit code 000 and A has got a 3-bit code 111, and move. There are 4 2-bit opcodes, move, add, subtract, like that, and they are having 2-bit codes. So you can say 01 is the opcode for move operation. 111 is the opcode for the A register to represent A register, and 000 is the code for B register. So the X code for move A comma B is going to be, just write all of them, 01, 111, 000. See, now combine the first 4, top 4 bits, 0, 1, 1, 1, that form the higher order X code 7. Then the lower order X code 1, 0, 0, 0, 4 bits are combined and that gives you 8. So B stands for the 0, 0 and this 1, 1, 1 for the A register and 0, 1 for the move. And finally you get the opcode, you see 7, 8. So it is a 2X code, 2-bit X code, and for the instruction move A comma B. So if you give the instruction 788, if you perform the execute the instruction, the microprocessor will understand and decode it to say that move the content of B register to A. While doing so, what is going to happen? The content of B will be copied in A. So the value of A will be erased, and you will see after the execution, both A and B will have the same value as that of B. So that is going to happen in the data transfer operations. Then hex code, to generate a hex code for move B comma A, instead of putting 78H, we have to put 47H. Why? Move has got an opcode 01, and here you see that B comma A, B comma A. B has got a code 000 and A has got a code 111. So if you combine the first 4 bits, you get the first nibble or the X code 4, and the last 4 bits combined gives you 7. So you get 2X code, 2-bit X code 47H. So 78H represent move A comma B and 47H represent move B comma A. So this is how we are getting the opcodes generated. I have given you a glimpse of that. Then coming to addressing modes. 8085 supports 4 types of addressing modes. It has 2 bits. It does 2 operations and it deals with 2 devices. It has got 3 types of instructions. And now you see it has 4 types of, it has got 5 flag registers. There are 4 types of addressing modes. So these are the numbers you must remember. 4 types of addressing modes. What are they? Immediate addressing, register addressing, direct addressing, and indirect addressing. So what is this addressing? See, when you go to a place, you must be able to commute from one place to another. That is from source area to the destination. You have to transfer the data. Our whole operation is data transfer. These are all coming in they are helping the data transfer operations. So we may have to move a byte of data from the source register to the destination register. So in this case, the source is going to be at immediate addressing. You are not going to refer to any of the registers. It is a constant data. You say move some constant value, 05 into accumulator. That is my requirement. Constant data is 05. Why? It is not going to change. Constant data is a 16-bit X code. Now 05 is a 16-bit data, X code, X data. In decimal it is 5. But in hex code it is 05. But it is a 8-bit data. That you must know. So it is a constant data. There is going to be variable data. So please note constant data 8-bit. 8-bit constant data can be moved to a 8-bit register. You must know that. That is very, very important. 8-bit register can be moved to a 8-bit destination register. Similarly, you can also have a 16-bit constant, 8050. or 1, 2, 3, 4. These are all 16-bit data or 16-bit address. So 16-bit address also is a 16-bit data initially, but it points to a memory register. So 16-bit data can be stored in a 16-bit register pair, HL, DE, or BC. So HL, they form the destination registers. So either A, B, C, any one of the 7 registers will be the destination for 8-bit operation, and these 3 register pairs, HL, D, or BC, form the register pair, 16-bit registers for 16-bit operation. Memory also we can, from memory also we can take it. So valid format, you see that move immediately. Previously we said MOV, isn't it? Now I'm saying immediate addressing. It is now coming under immediate addressing. Because of immediate, you get that I. Move, MVI is another mnemonic. You see, MOV is one mnemonic for move. MVI is for move immediate. It means it is going to handle only constants. What is a constant? It can be a 8-bit constant or a 16-bit constant, which will not vary during the execution of the program. So that way, the constant data can be either 0, any one of the value from 008 to FFH. So that way, 05 is one of the example of data 05, and that has to be placed in A. A is my destination register. So MVI, comma, immediately it is a 05 data. See that MVIA is an opcode which will occupy one memory location, 1 byte. And 05 is a data which will occupy one memory location, 2nd byte. So it is a 2-byte instruction. Data occupies 1 byte and opcode occupies 1 byte. So totally 2 bytes of data are played in, it's a 2-byte instruction. Similarly, when you come here, MVIM, this memory location 05, data 05 can be placed in memory. M, what is it? It refers to HL register pair. The content of HL register pair is pointing to the memory location. So you can directly place 05 in the memory location pointed by HL register pair. So that is why you say MVI M05. So the data can be placed, 8-bit data can be placed in a 8-bit register, or 8-bit data can be placed in memory also. Memory location pointed by HL register. It's a 8-bit data. Similarly, when I come here, 16-bit data, it's 8050H or 1234H, they are all 16-bit data, which they have to be placed in a register pair like HL, DE, or BC. This I have taken it as, for example, HL register. So we have a new mnemonic called LXIRP. So MVIR, that is the general format, MVI register, comma, data. Here MVI memory, comma, byte of data, XX byte. But when I come here, LXI RP, instead of register, we write RP. LXI, load immediately. Here we say move immediately the byte of data into the register. Here we say load immediately. X stands for a register pair. Immediately into the register pair. Whatever register pair, here it is H. So move the data. It's a 16-bit data, double byte. So LXI RP DB. We say DB or 4x. That means it is a 4-nibble data, 2 bytes of data, 16 bits of data can be moved into a register pair. In this case, register pair, I represent the H. I can also say LXI D, 1234H. In that case, the data is a 16-bit data. So you should remember when I put I, or if you are dealing with immediate data, you have to go for immediate addressing. So 1234 is a 16-bit data which is placed in LXID. D register. So D will occupy 1, 2, and E will occupy 3, 4. So that way is LXID can be used for storing a 16-bit digital data in the register pairs. So it is immediate addressing. Remember, it deals with constant data. Whenever you want to have 16-bit data introduced into a register pair or 8-bit data introduced into a register, yes, you think of immediate addressing. Or if you see immediate addressing instruction MVI, then immediately think that you will have a 8-bit data which will be placed in a register referred here. Okay, so we'll go. This is the starting point. So immediate addressing. Then we'll go to the second, register addressing. Second type addressing mode is register addressing. That means register to register contents. The content of one register is moved to content of another. You see, we don't know what is the value to have in that register. So it is addressing mode fit for variable data. The data of the register the content of register can change, can be incremented or decremented. It need not be the same in the execution of the program. So during the execution of the program, the 8-bit content of any 8-bit register can change, either incremented or decremented or change. So that way it is called a variable data. So the variable data must be stored in a register only. So it can be either a register or it can be a register pair. So in this case, register addressing deals with variable data. The content of the data will vary from 00 H to FFH. So the source, there are now 2 registers. From one register, 8-bit variable data register, to another 8-bit register, source register and destination. The format is move register 1, comma, register 2. The content of register 2 is a 8-bit register, will be placed in the register 1. So you see move A, comma, B, which I have already explained. The content of B will be placed in A. Move the content of register 2 into register 1. 8-bit data, copy and paste. Addressing modes. Third addressing mode, direct addressing. Now, if you, so far we were dealing with the immediate byte of data with the register, data transfer, or content of one register to another register within the CPU. So data transfer within the CPU are addressed by first two addressing modes, immediate addressing and register addressing. When I come to data transfer between accumulator and memory, special accumulator and memory, any register and memory, you must remember that. Between this two-way communication. From memory, it can come to accumulator. From accumulator, it can go to memory. Similarly, from accumulator and memory. So, if you any register also it can come from memory to any register. That we will see later. So, memory to accumulator. Then you have accumulator to memory. These are all allowed. See, when we talk about memory and CPU transfer, data transfer between the memory and the CPU, yes, memory to accumulator only comes, accumulator to memory. They are allowed. But from M1, one memory location to another memory location, we cannot transfer. Transfer between memory 1 to memory 2 is not permitted. So that you should remember, valid format. Now we are going to the third mnemonic called LDA address. So direct addressing, load accumulator directly from the memory address given in the instruction. See, the address is given in the instruction. It is a constant. This cannot change. If you think that you are very sure that the address is only 8050, it's not going to change. It did not have to change in the program execution. Then you use the direct addressing. There are two. That is for bringing the data from memory to accumulator. LDA loads the content of memory location addressed by the instruction here. Address to accumulator, load accumulator directly from memory 8050H. The reverse is store the content of accumulator into the memory, say 8060H. So LDA 8050H means you load the content of 8050. Let us say 8050H has a value 05. We don't know. It is there. Now when I say LDA 8050H, the content of memory location 8050, which is 505, is brought to accumulator. So after the execution, the accumulator will have the value 05. So it is LDA address means you are bringing the data from memory, 8-bit data. It is 8-bit. From we have got 16-bit operations, we will see. So LDA 8050 refers to that source and destination. From memory, it comes to accumulator. If this is from 8050 memory, it comes to accumulator. Next instruction, if you write like this, STA address STA 8060H. So that way, you are saying that store the content of accumulator. What is 05 is in the accumulator. You store it back, isn't it, into memory. From the accumulator, you take it to memory location 8060. The content of accumulator will be placed in the memory location 8060H. So after performing these two instructions, you see that the content of memory location 8050, which is M1, is placed in the memory location 8060H, M2. So this is what it's not permitted. In a single instruction, you can overcome that problem by writing two instructions. This way, LDA address, you bring it from memory to accumulator, and from accumulator, you take it back to the different memory location, M2. So that way, this is 8-bit data. What is not permitted here is overruled, or we can overcome the problem using these two instructions. So these are all about 8-bit data transfer. Now, 16-bit data transfer between HL and two consecutive memory locations. Here I said memory to accumulator. Then when we come to indirect addressing, we will see that memory to any register. So direct addressing allows only between memory and accumulator and memory. When I go to indirect addressing, it allows memory to any register to provided HL is used as a memory pointer. So indirect addressing is a little difficult. Let us see. But here we have overcome the problem. LDA address, ST address is we are able to transfer the content of memory location 1 to content of memory location 2. The content of 8050 is taken to 8060H. So these are all 8-bit operations. When I come next, it is 16-bit data transfer. If it is 16-bit data transfer, 8-bit accumulator is 8-bit accumulator is A register, whereas a 16-bit accumulator, always between accumulator, direct addressing means accumulator and memory. Okay, if it is 16-bit, it has to be two consecutive memory locations. But the destination has to be an accumulator. Oh, which is the 16-bit accumulator in 8085? They will ask, I will also ask whenever I go for interview. So this way, 16-bit accumulator available in 8085 is HL. So that way, 16-bit two consecutive memory location data can be brought to HL register pair using direct addressing. What is the instruction? LHLD address. And the reverse is SHLD address. For example, address is 8050H. Okay, 8050 has 1, 2, and 8051 has 3, 4. Let us say we are putting 805051 value 1, 2, and 3, 4 will be in 50 and 1, 2 will be in 80. So this is how the 8050 memory location and 51 memory locations are loaded with 3, 4 and 1, 2. Now you execute instruction LHLD 8050H. You're referring to the first memory location, not the second one. So 80 LHLD load, not accumulator, HL register pair directly. See, it is very similar here. LDA, here it is LHLD, load accumulator. Here it is load HL register from the memory locations, 2 consecutive memory locations presented in the instruction. So 8050 and 8051, 2 memory contents will be brought to HL register only, not D or BC. This is important. Then say SHLD, just like STA address, the content of accumulator is taken to the memory location 8060H. Similarly, the content of HL register pair, it is a 16-bit data, so HL register pair will be transferred to 8060 and 8061. So 1, 2, 3, 4. You will see that 3, 4 will be in 8060 and 1, 2 will be placed in 80. So this is how we can have data direct addressing scheme to perform 16-bit data transfer. Now coming to indirect addressing. I told you indirect addressing means the address is not specifically given in the instruction. Direct addressing, the address is not going to change. So we call it as a constant data and put it in the instruction itself. Whenever we execute the instruction, the data will be either taken from that instruction only or stored in that address only. So indirect addressing allows variable memory address. So 8-bit data transfer between memory and accumulator or any register. See, the address has to be varied. If it has to be varied, you have to allow the address to be varied. That is what I say. Then you have to have a 16-bit register holding the address. What are they? We have DE is one 16-bit register referred as D register. And this is XD refers to D register pair. X means 16-bit. So 16-bit DE register pair or P. So DE is one set. And then BC is another 16-bit register. And finally, you have HL is the memory pointer. We also use it as H register. See that if address is placed in D register, that's what I have written. The instruction has to be LDAXD. And if it is LDAXD, what happens? You are going to load the accumulator from memory location pointed by the D register. See, XD is replacing the address. Previous slide, if you refer, LDA address. Instead of address, I am writing XD. So I am referring to a register pair XD, saying that the XD register, D register pair holds the address. So first you should load into the D register pair and then you have to introduce. So first you have to define the D register pair, then you write LDAXD. By doing this, you are going to gain a lot of advantage. What is that? LDAXD. The register pair can be changed next time. In a loop, if you put it, the D register pair can move from 8060 to 8050 to 8051, things like that. So LDAXD allows the D register pair content to change. Therefore, the instruction fetching instruction operation will be done from new memory location, LDAXD, from memory pointed by the D register pair. You take it to accumulator. Similarly, STAXD, we can skip here. STAXD is reverse. You store the content of accumulator into the register, the memory location pointed by the D register pair. So the operation is reversed. From accumulator, it goes to the memory pointed by the D register pack. Similarly, BCA acts as a memory pointer here. So memory pointers, we have three types. DE is that and BC. But in all this, DE and BC refers to accumulator and memory only. Accumulator memory, memory, accumulator, accumulator memory. It does not permit any register. So if you are interested in transferring the data from memory to any register as well as accumulator, then we will go for HL. So this is the order of preference for memory pointers. First we say HL is the memory pointer. Yes. The next will be DE is your memory pointer. And the third BC will be your memory pointer. This is the order in which we define. So HL, if HL is the memory pointer, it is referred by a single register named M. So we say not that LDA, XT, ST, this is LDA address, STA address, LDA address, STA. Here it is move A, comma M. M is the address pointed by HL register. It's a memory location whose address is in HL register. Move A, comma M. Move the content of memory location pointed by HL register pair to accumulator. So move A, comma M is similar to STA address, LDA, XT, LDA, XP. These are all similar to move A, comma M. Similarly, STA, XT, STA address, STA, XD, STA, XB will be similar to move M, comma A. From accumulator, you move to memory. From memory, you move to accumulator. Here, from accumulator, you move to memory. But the HL is the pointer. That's why we use the letter M. Here, because HL is a memory pointer, special memory pointer, we can, instead of writing A, we can put any register. This is also allowed. Move register pair, register A, 1, A to 7. There are 7 registers, A, B, C, D, E, F, E, F, and HL, D, E, and HL. So you can put move register, comma A. Any register, move B, comma M. You can have an example. In that case, the content of memory location will be moved from the memory location pointed by HL to B register. The destination register can be a memory. It can come to, the destination can be any register. So that is the advantage of using HL register pair. So we have got 3 memory pointers, DE, BC, and HL. HL is referred by letter M, and the mnemonic used is move A, comma M, similar to move A, comma B, like that. And this is similar to LDA address, STA address, D and BC. See that these are all single byte instructions. You must know that LDA address is 2 bytes, LDA is 1 byte. So they are 3 byte instructions. Single byte, 2 byte. Move A, comma B is a single byte instruction. MBIA, comma 05 is a 2 byte instruction. And here you see LDXT, STXT, they are all single byte instruction. Move A, comma M. So this is the advantage of having. Now we have come to programming techniques. That way, first let us say we want to move a byte of data 05 into accumulator. So that is our aim. How are we going? In 4 addressing modes. There are 4 addressing modes. We are doing the same task. Move a byte of data 05 into accumulator. So accumulator should have 05. So the 05 can be immediate data. In that case, MBIA 05, immediate addressing. It can reside in B register. In that case, move A, comma B. And if 8050H has 05, then LDA 8050H is the correct instruction to load accumulator with 05. So the memory programming techniques, yes, to move a byte of data, immediate byte, register content, memory content. So these are the different techniques which I am going to deal with. Let us do it fast. Programming. To move a byte 05 into accumulator is indirect addressing. So we have seen three of them, direct addressing, immediate addressing, register addressing, and immediate direct addressing. Now in indirect addressing, if when you come to indirect addressing, there are three memory pointers. Any one of the pointers can be pointing to the memory location. If you consider DE, register pair is pointing to the memory location, it is the memory pointer, then we use LDAXD, that's all. When you say LDAXD, the content of memory location, we assume 8050 has 05, therefore the 05 will be moved to accumulator. If the BC register pair is acting as a memory pointer, you use the instruction LDAXB. Here we see that XB is also having 8050, mind that XB is also having 8050H, and the content of 8050H is 05. Then the content of memory location 8050, which is 05, is moved to accumulator by the pointer B. So the memory pointer indirect addressing, we have three pointers, DE, BC, and if HL is going to be the memory pointer denoted by M, then we use move A, M. So we see we are now thorough with data movement in between the accumulator and memory, between the registers. Then comes the next technique. We may have to clear the accumulator. How are we going to clear? There are four ways of clearing the accumulator. I may go a little faster. MVIA 00 is you are using a data transfer group. We can move immediate data into the accumulator. MVIA 00. That way you can clear the accumulator. The content of accumulator must become 0000. In doing this, after execution, none of the flag will be affected. So data transfer group instruction does not affect any of the flag. None of the flag is affected. So that is the advantage of using data transfer group for clearing the accumulator. When I come to the next one, sub A, subtract accumulator content from accumulator. It is an arithmetic group. AC, CY, carry flag, auxiliary carry flag, Z flags are affected. Affected in the sense, if it is 0, it will become 1 accordingly. Z flag and AC and CY flags will be changing. XOR AA is a logic group. Here you see a very interesting thing. It not only clears the accumulator, see logic group, it clears the accumulator along with AC and CY flags. The auxiliary carry flag and the carry flag are also cleared along with the accumulator, and the Z flag is set. Then you see ANI 00, it is also a logic group, and immediately the content of accumulator with 008. In that case, again, AC, CY, Z flags are affected. So there are four different ways we can clear the accumulator. This is also a short note question, so you must know that. Then to clear a 16-bit accumulator, which 16-bit accumulator is HL. So use the immediate addressing, LXIH 000H. So HL value becomes 0008 and it is cleared. So clear 16-bit accumulator. To clear two successive memory locations, what will you do? You have got one memory location to be cleared, use LDA, STA, that's all. Not LDA, move immediately accumulator MVIA, 00 and STA address. Whereas two successive memory locations, 8050 and 8051. So that means LXIH 00H, first instruction, then SHLD 8050 refer only the first memory location. That means the 8050 will be placed 00 as well as 8051 is also placed 00. We are able to clear. So when I place 00 in the respective registers or memory location, we have cleared the destination. To move a byte from, okay, from one memory location to another. So we have already done this. LDA 8050, STA 8060. We will be able to move the content of one memory location to another. That is, both the memory contents M1 and M2 will hold the same data after the execution. It is called copy paste. this instruction, copy, paste in your computers. So the content of memory location 8050 will be copied in 8060. So 8050 as well as 8060 will have the same data, XX, whatever it is, they will have the same data. Then to move a byte from memory 1 to memory 2, using memory pointers, employing, yes, sir. So memory pointer, use memory pointer, HL and DE. So previously we used direct addressing from memory 1 to memory 2. Now, how will you move a byte from memory 1 to memory 2 using memory pointers? Let us say HL points to memory 1, 8050. DE points to memory 2, X0. How can you say that let HL point to 80 by making LXI H8050? When you execute this instruction, so this is called predefining the HL and the DE register pairs. LXI H8050H, you are defining, you are making the HL point to 8050H, the first memory location. Then when I say LXID 8060H, DE points to 8060H, that is memory 2. Then move A, M. Content of M1 is copied in A. You bring the content of first memory location to accumulator using the instruction move A, M, because HL is the pointer. Now you see we have started using the instructions move A, M. Content of memory location pointed by HL, that is 8050, that will be taken to accumulator. Then STAXD, move the content of accumulator to the memory location pointed by the D register pair. So the content of memory location M1 is copied in memory location M2 using indirect addressing mode. So different techniques we must know. Then exchange. Exchange is different from data transfer. When you transfer, I told you the previous data, the destination register will get erased. It will lose its previous value. The source data will be occupying the destination register also. So when I say exchange, I have to retain both the registers, A and B. If I want to exchange, the content of B register has to come to A, and the content of A register has to go to B. I cannot simply say move A, B. In that case, the content of A register is lost. So what we do, we have a temporary which is, I am now, register 1 is B, register 2 is C, sorry, register 1. So between B and C, we are exchanging. B and C, the content of C is taken to B, and the content of B is taken to C. So A, accumulator is used as a temporary register. Move A, B, the content of B is taken to A, and now you see A will have the B value, and now the C register content will be taken to B. Doesn't matter, it gets erased, but C data will be in B. And now A has the B register content. Therefore, from A you move to C. So that way we have exchanged the content of B and C register using accumulator as a temporary register. Between two memory locations, use A and B as temporary registers. Move M1, the memory location 8050 and 8060 have to be interchanged. That is exchange. You know, these are the techniques, no? If you know all this, you know how to drive in the crowd also. Left hand, right hand, robo we teach. And once that is done, then we can take it to the crowded area also, your robos. So like that, LXI H8050 HL is now pointing to memory 1 and D is pointing to memory 2. And move M, B. See, I am directly taking the first memory location to B register and saying that LDAXD, the content, memory 2 is brought to accumulator. The second data is brought to accumulator. The first data is taken to B register. Then you say exchange. When I say exchange is another important 16-bit register. The content of D and the HL will be exchanged. So now D will be pointing. HL means HL will be pointing to memory location 2. D will be pointing to memory location 1. That means HL will have 8060, D will be having 8050. So in that case, move M comma B means the content of B, which was previously in memory location 1, will go to memory location 2, and STXT will take the content of memory location 1 to memory location 2. So these are the different techniques. Then to exchange the content using push and pop instruction, I told you, you have an instruction called exchange. Exchange is a single instruction which will exchange the content of DE with HL. You need not have to do anything. We know for transferring A, B and C, we need 3 instructions. Similarly, if you want to transfer HL with the DE, we may need 6 instructions. But an exchange instruction, a single instruction, can do that operation of the 6 instructions. Okay, so that is with exchange. Exchange allows only HL and DE to be exchanged. If you want to exchange between HL and BC, then you have to use 4 instructions: push H, push B, pop H, pop B. Here, push H means you are pushing the content of HL to stack. Then followed by push B, you are pushing the content of BC to the stack. So now the content of BC will be the topmost on the stack. So when you pop, the content of B will come and you are popping into H. That means HL register will receive the BC register content. And when I say pop B, the second data will be popped up, and that will, the HL content will be placed in B. So this is how we do for pushing, exchanging the content of HL with BC, and similarly BC with D. Then you have shift left the contents of B register using RLC. Shift left is another important operation which may require, and that is done with the instruction called RLC. Move A comma B. First, you know that the RLC instruction can be done, performed only in accumulator. So if we say content of B register, purposely I have put B register, not A register. If it is B register, first the content of B register has to be taken to accumulator and then perform RLC. When I perform RLC, the content of B register will be shifted left 1 bit position and it will remain in the accumulator. So the accumulator content has to be pushed back, taken back to B register. So move B comma A. The result of shifting left 1 bit position is equivalent to doubling the content of B and also multiplying the content of B by 2. So these are the expectations that we can have with the shift left operation. Then comes shift left the content of BC register by S. Multiply the content of BC by register pair 2. Use HL register pair as 16-bit accumulator and use that. So now we are going to have 16-bit. Okay, doesn't matter. LXIH, the 00 clear accumulator, DAD H, load BC into HL. Okay. Multiply. Oh, yeah. DAD H and DAD B. Right. So here we are going to shift left the content of 16-bit register BC. Shift left the content of BC register. BC is a 16-bit register. We want to shift left. So we have to now bring the BC content to 16-bit accumulator, which is nothing but HL. See, HL is a 16-bit. First I clear LXIH 000H. I clear the accumulator, 16-bit accumulator. Then I perform DAD B, double addition. That is, the content of BC will be added with HL. So the content of BC is now brought to HL. Please see that LXIH is made 00. I clear the 16-bit accumulator, HL, and then I perform addition, double addition of BC with HL. So that means I am bringing the content of BC to HL. Now I say DAD H. I add the content of HL with HL. That means everything gets shifted. Double addition. I told you, no, shift left operation. So reverse. So we are shifted left 16-bit content of HL register pair here, which is nothing but the BC register pair. But the result is available in HL register. So you have to take it back to BC register pair. For that, you say push H and pop B. So the content of HL register will be pushed to the stack and it is taken from pop from the stack to B register. So the BC register pair now will have the 16-bit register will have shifted left operation. Then to access the content of SP, these are all the applications of DAD. Okay, to access the content of SP register with pair in DE. So SP register is not accessible to the user, but you can find the content of SP by doing the same thing. LXIH00H, DAD SP, and then exchange. DAD SP means you are going to add the content of SP with HL. Therefore, the HL is now going to have the content of SP, whatever the value. And if they say exchange, the content of SP, which is in HL, will be taken to DE register pair, where you can find out the actual value of DE. Addition of 8 bits. So you see, N is number 5. Indirect addressing with HL register. N is equal to 5. Number of 5. 5 N bytes of data. How are you going to add? You cannot be simply saying add, 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 add. So let us put it in a looping. So I'm going to demonstrate looping operation. Let N is equal to 0, 5. N bytes have to be added or stored from M0 8050H. So the data is stored from 8050H. We store N is equal to 0, 5 in C register. Since we have to add 5 times, this is a loop operation. Load HL with 8050H so that it acts as a memory pointer. So the data location is 8050 and that is pointed by HL, LXIH 8050. We have to perform 5 add operation. So we have a counter MVIC, 05. So to start with, I have to clear the accumulator and the carry flag and the auxiliary carry flag. All of them, because the addition operation, I have to clear all of them. So for that, I am not using MVAA 00H. Instead, I am using XOR AA. So this way, accumulator is cleared along with carry flag and the auxiliary carry flag. So once the accumulator is cleared, I can bring the first data. So LXI HL is pointing to 8050H. So when I say add M, the first data will be added to the accumulator. Then INXH, that means the HL point is increased to 8051. So now it is ready with the second data. Decrement, we have done one addition operation. So decrement C register, number of bytes. So J and Z repeat. So if until it becomes 4, it's 0, J and Z. Repeat until it becomes 0. So jump not 0, you jump. So when the Z flag is not set, you jump to 810, repeat addition operation. So you see that add M every time till, so 5 times when you add, Z and Z becomes 1 and it will fall through. So instead of repeating addition operation, it will fall through and there you want to store the result in next memory location. So INXH, you prepare the pointer to point to the result area. So INXH, then now the result is in accumulator. Move it to memory so that you can store it in memory location 80, whatever the value, last after 5. So 8056, you will have the result stored. So that way, N bytes can be added. Block move. So here we are going to add a set of numbers, say a group of numbers starting from 8500H pointed by HL to a new location 8600H. We are going to move some 10 bytes of data from source location 8500H to new destination address 8600H. So what we do, we use HL pointer to point to the source location 8500. Then we use a DE pointer as memory point, D register as a memory pointer. LXID 8600H points to the new destination location. Now we have to move 10 bytes, so we put MVIC 0AH. Then we perform the instruction start. Source data is brought to A, move A, M. STXT, source data is placed in destination location. So you take it there. Then INXH, INXD, you increment the pointer to 8501 and 8601 so that you are ready for the second byte. And decrement, you have done one operation, only 10 operations you have to perform. Decrement C till it becomes 0. repeat the move operations. So you are moving and incrementing. These 5 steps are done repeatedly 10 times. And when Z flag becomes 0, when the content of C register becomes 0, Z flag is set and it comes halt. So this way it is able to block move a group of 10 bytes, counting number of ones in memory. So we have to count the number of ones in a register, in a byte. So for that, see that HL is pointing to the data, 8100H. We have C register as the counting. And now we have to move initial count. How many ones are there? So count register C is initialized as 00H. And we have to rotate 8 bits. So that for rotating 8 times, bits must be rotated. And as we rotate, the MSB bit will go to the carry. We check on carry. If the carry is 1, we increment the C register. If the carry bit is 0, we skip and then go to the other next data. So that is the procedure. MVIC 00H, MVIB 08H, move A, these are all initialization. And then move A, M, you bring the first data to accumulator RLC. So that the data is brought to accumulator. When I perform RLC, the MSB bit goes to the carry bit, jump no carry. If there is no carry, you move to the next. That is, you skip incrementing the counter. If it is 1, then fall through, increment the counter. So you have performed one operation. So decrement the number of bytes. So 8 bits. So B register is decremented till 8 rotations are given. Jump no 0. Where till B register is 0, you move RLC, repeat this operation. When 8 operations are over, jump Z register is set. So it comes down, it falls through. You increment to the next location, and you know the C register will contain a number of ones in the byte. So that can be, that is the result. So you have come to the result location 8101, and the number of count C register is brought to M. So this is a counting of number of words. Then to multiply or divide the content of C register by 8 without using add operation. We must say multiplication is repeated addition. For that, we have to necessarily use add instruction. But the question says how you can do that without using add instruction. Use RLC. See, for 8, you have to rotate left 3 times. That's all. Because each time you rotate, it doubles. So you see, you move the content of C register to accumulator, rotate doubles, then 4 times, then again RLC, it becomes 8 times. The result will be in accumulator, move to C register. Similarly, by divide, for divide, you have to perform the opposite operation, RRC. Here, the content of C register is taken to A, maybe 8, then RRC will make it 4, then next RRC will make it 2, and now this will be, so you are dividing by 2, dividing by 4, dividing by 8. So that way you are able to left rotate right is equivalent to dividing, and therefore we can use RLC and RRC instructions for multiply and divide. Then access the content of auxiliary carry. Auxiliary carry flag we cannot access. There is no provision here. In 8051 and 8086 we have the provision. For 8085, there's the only way. We know that the flag register forms the lower byte register in PSW. PSW is the processor status word. The higher order register is A, and the lower order register is the flag register. And when you come to the flag register format, we see that auxiliary carry occupies the D4th bit. So if you rotate 4 times, the auxiliary carry 1, 2, 3, 4. 4th time when you rotate, the auxiliary carry goes to the carry bit. So by checking the carry bit, we will know the status of your auxiliary carry flag. This is what is done here. Push PSW, pop B. So you are bringing the flag register to C register. So it is available in the C register. So move that to accumulator because that has to be rotated 4 times. So move A, C, RLC, RLC, RLC 4 times, and that will see that the carry flag is in the carry, auxiliary carry flag is in the carry flag which can be accessed. To swap the nibbles of C register, use RLC 4 times. That is, swap means you are moving the lower nibble to the upper nibble. You can do it this way, or upper nibble to the lower nibble. You can use move A comma C. The content of C goes to A, RLC 4 times RLC, and move it back. You are swapping the nibbles. To mask the MSB bit of C register, so take it to accumulator and immediately with 80. When I say mask, that particular bit must be 1. So you say MSB bit, you put 1, remaining 0. So A will make all the bits 0 except the MSB bit. If the MSB bit is 1, it will remain as 1. And if it is 0, it will become if it is 0, that is also 0. 1 and 0 added will give you 0. So by checking the content of C register, whether it is 0 or not, or 1 or 0, we will know that we have masked it. We will know the content of the MSB bit. To mask the LSB bit, we do it like this. ANI, the code is changed. It's 800001. So ANI with 01. So that will give you masking of LSB. Multiply the content by 7. Previously I said 8. 8 means 3 times rotation will give you multiply by 8. Again, you subtract the content of C from the accumulator. It gives you 7. Therefore, you move it. So that way, we can perform multiply by 7 also. To add the contents of this memory location, I think we can do that up to 100. See, there are many things now. Add the content of memory location 50 with 51, B register content, and immediate data. See, 8050 is pointed by memory location. So move HL register pair, move A comma M. The content comes to the accumulator, INX H. Add M so that you are adding the next memory location. Then add B, you are adding the content of B. Then you are adding 100 is a decimal number, so convert it to 64H, hexadecimal, and add 64H. Then INXH move. So you are able to do that also. To add two 16-bit data using that. See, two 16-bit data, number A, number B are added. Number A is in 8050 and 51, and number B is in 8060 and 61, and number sum will be in 807071. See, well, number A is 1234, number B is 7856. Okay, number A is available in 8050 will be 34, 8051 will be 12. So 1234 will be stored in memory location as 34 and 12. Similarly, the number B will be stored in memory location 8060 as 56 and 78. Lower nibble first, higher byte next. And then the result is going to be when you add 6 plus 4 A, 5 plus 3 8, 8 plus 2 10, so A, then 7 plus 1 8. So 8A will be in 8070 and 8A will be in 8071. For that, the program is LHLD 8050A. You are bringing the content of 8050 and 51 to HL. Exchange. So when I say exchange, the content of 8050 is taken to exchange. D becomes LHLD 8050. The HL is brought to the 8050 content is brought to HL, and now the content of HL goes to DE. Okay, so we have stored the data in DE down. Then we say LHLD 8060, we are bringing the second data. See, we have only one 16-bit accumulator. So LHLD 80 is the only instruction. So we are bringing the number A to HL first. Then when I say exchange, it is stored in, saved in D register path. Again, we use LHLD direct addressing 8060 so that we are bringing the number B, second number to HL. Now the second number is in HL, the first number is in D. So we perform DAD D. So when I perform that, sub is available in HL. And now you say SHLD 8070, the sum is placed in 8070 and 71. See, very powerful instructions which can perform 216-bit. Hexadecimal, which is only for main decimal things. So we have IO decoding, very, very interesting. So we have so far dealt with memory operation, data transfer and addressing modes, and how to handle addition, subtraction, and so many other things, shift left, and different techniques we have studied. And now that is all connected with the CPU. Now, when you are going to interact with input-output device, we have to interface. So this will be helpful for your projects and interfacing experiments. So there are three types of I/O operations: hold I/O, interrupt-driven I/O, and DMA transfer. Hold I/O is fixed using fixed decoders. Interrupt, you say input and output will have ports, and the data will be transferred from the port to accumulator, or from the accumulator to the port. Similarly, this interrupt-driven I/O, whenever interrupt comes, the I/O operation will take place. DMA transfer, for transferring a large amount of data from memory to another auxiliary storage capacity, or from auxiliary storage to the online memory location, we use DMA. So when I come to hold I/O, there are two operations, two types, which is direct I/O and memory mapped I/O. Here I will be dealing only with direct I/O, because memory mapped I/O gives you large number. Only when you need more than 256 ports, we have to go for memory. Here you will be making use of 16 address lines. Yes, 16 address line A0 to A15, and it will give you 64,000 input ports and 64,000 output ports. Port is nothing but a 8-bit latch, and it is also considered as a 8-bit register with chip select, because we know memory registers. So port is also nothing but a 8-bit register, and also we call it as a latch because it has got a chip select. So this way, direct addressing. Number of address lines for direct addressing is only 8. Either A0 to A7 or A8 to 15 will be used for decoding purpose. So that way, 2 power 8 is 256. So you have got 256 input ports and 256 output ports. Port address ranges from 0 to 256 because it is 2 power 8 address. So you can ask a question, sir, can we have address from 00H to FFH for input ports as well as output ports? Yes, sir. That question has to be addressed. For that, the direct I/O decoding, 8 address lines serve as the inputs to a decoder. The output of a decoder is called device address pulse select. Device address pulse ANDed with the appropriate control signal, IOR for input port and IOW bar for output port gives device select plus. So from the 8 address lines, you have device address line, address select. You have address select line, and then you have got device select lines. So these are the three things you will see them. The input or output port connected to the peripheral device. The ports are now connected to the peripheral device. Microprocessor, in between you have these ports, and the other side of that will be your peripheral devices. So you give 8 address lines, and the decoder will select only one address line. That means one of the 8, 2 of the 6. One of the 2 of the 6 ports will be selected, and that becomes the device address first. And that, when it is combined with the control signal, becomes a device select pulse. It can be an input device or output device. So address and operations are decided here. The address lines decide the address of the port. So the which address, the decoder provides that address for the port, and the appropriate control signal, IOR bar or IO memory bar, decides whether, that is the control signal, decides whether the port is input port or output port. Input port or output port can have the same address in 05H or out 05H. So that is why the question is now again is that see in 05 out 0F. That means you are inputting through 05H and outputting through 0FH. But you can also have in 05H, out 05H. So how this is problem solved? See, the address is decided by the address port, address lines to the decoder. Similarly, here, address is same. Whereas when you say in and out, you have the control signals changing. So when you are handling input IO R bar line will be ANDed. For output, IO W bar line will be ANDed, and therefore you get the output port with the same address. Let us see. Here you have the example. IO decoding circuit using NAND as decoder network, port address 80H, output port as output port. So the address has to be 80H and the port has to be output port. What is the design? So you come this way. The NAND gate, we are using 8-bit NAND. So A0 to A7, only 8 address lines we are using. A0 will be 1, the remaining things are 0. So A0, A0, I think this is not 80, it is 01H. The address is 01H. So all of them are 0, sorry, A0 is 1. So in that case, the address is 01. See, when the zeros are going there, this is going to be inverted and you will get all the 1. The NAND gate output will become low when all the inputs are 1. The NAND gate output will become low when all the inputs are 1. Your address is 10000. So it is 01H. When 01H is placed to the decoder, then you see that 1 comes here, 0 is converted to 1. So all the 8 puts only for this combination, 01H, this NAND gate will go low. So like that, 256 8-bit 8-input NAND gates are there, and one of them will have this connection, next it will change. Like that, we can have addresses from 00 to 01 to FFH. All that can be having 256 8-input NAND gates will form the decoder section, and for us, we need only 01H, not 80, 01H. The output, it has to be output port. Output port means LED. So this is the LED, not a keyboard. Keyboard is the input port. This is the LED. So you have an enable. This enable line, the data from the processor will go. So from the accumulator, the data will go into the latch and it will wait. When the this is input line, output. So IOR bar line goes low. The IOR bar line is connected here. Till then it will be high. You have selected the address 01. That means this has gone low. So this has come here. When it is 0, it will be 1. It is becoming 1. Whereas your IO right bar will be still high. Therefore, this is 0. If this is 0, output will be 1 only. But it will wait till IO W bar line goes low. When it goes low, this becomes 1. This is already 1. So when both the ones, output will become high, and that way your latch for the input port address 01H. Sorry, this is an output port. The data will go from here to the LEDs. So when the enable light goes high, data from the accumulator will be transferred to the output buffer lines. Therefore, the LEDs will burn. So this is the decoder arrangement for output port with address 10H. Now, can we have the same? That is the question. For 4 to 16 decoder is used here. The lower address A0, A1, A2, A3 are connected here. And you see that the higher order address lines A4, A5, A6, A7 are connected to the 4-input NAND gate. We know the same address, I think the address is FFH. FFH is here and FEH is given, F5H is here. So if I want to take FFH, let us see what happens. F5H I can finish. Sorry, okay, FFH. FFH means all are ones. So here, A0, A1, A2, A3, all are 1. Then the 15th line will go low. Say 4 to 16 decoder, outputs will be 16, input will be 4. Then the A, B, C, D are the input for the decoder, and they are given the lower order address lines A0, A1, A2, A3. Therefore, they select output 15. So you see, you have selected pulse. F of H is the address at this point, and it has to be output port. If it has to be output port, you connect IO W bar line to this So for when this goes low, this is 1. When this goes low, this is 1. And therefore NAND gate becomes high, and the output latch for the output port with address FFH will be enabled. So you will be able to have the transaction done. Similarly, for output port F, this is output port FE. This is IO R bar input port. They must have put input port. So that way, for FE, you change the address, it will select. Now let us come to F5H. F5H will be you FF, all the 4 bits of the nibble, higher nibbles will be 1, 1, 1. So all of them are 1, output will be 0, the chip is enabled, and then comes 5. So when I give 5, F5 will be, 5 means 0, 1, 0, 1. So that way, when you give, this output line will go low. When the output line goes low, address is F5H. If you connect it to IOWR bar, it can go to the LED output, so that it is an output port. So the output port with the address F5H. The same output, see that the address lines decide the address of the port. So with the same address line, decoded address line is connected to this AND gate, and IO bar line, the control line is given here. So the output will go low only when IO bar line and F5 goes low. So that way we are able to input the data from the keypad port to the accumulator. So microprocessor. So this way we can have the same address F5H for the input port as well as for the output port. The control signal IOWR bar and IOR bar decides this operation. Then instead of decoding, I said about 256 8-put ports must be there, and of course we are using only 1 or 2 ports. We may have that NAND gate arrangements, but in the market we have got 8255 programmable peripheral interface chip is available, which has got 3 ports available: port A, port B, port C. 8-bit ports it provides, and it can be interfaced. So your input device as well as the output device can be interfaced to the microprocessor through this 8255. So 8255 chip comes into the picture. Microprocessor provides the address and the details of the data taken from the port to the accumulator or from the accumulator to the port, and the input ports devices are connected to the input port. You have got input port here, port A, and you have got port B, which is serving as the output port. So port A is designed as input port, port B is designed as output port. So that is called programmable peripheral interface chip 8255. The next slide, you can see the 3 ports of port A, port B, and port C have 8 lines each. The 8 bits port C is divided into 2 groups of each. Okay, and so you have got here. You see that port A is a 8-bit port, port B is a 8-bit port. At the same time, port C has got PCC, port A, PA0 to PA7, and PB0 to PB7. These 2 are 8-bit ports, whereas the port C has 4 ports, 4 bits. PC0 to PC3 form the port C lower, PC4 to PC7 form the upper PC. So PC upper. So this way, the 8255 can be programmed. We can program it as it is available. It can be programmed in IO mode as well as BSR mode. BSR mode means each bit can be set or reset, but it will affect only the C register, C port. Only the C port, port C will be affected by BSR mode. Single pin will be affected, either set or reset, the bit set. Here IO mode is for byte operation. 8 bits will be affected. It is called a simple IO mode operation. Mode 0, simple IO operation. Mode 1, input output with handshaking. Mode 2, bidirection. So let us see how IO mode can be used here. Says port selection. First, you must name the address of the port. Addressing the ports. A0, A1, and the chip select pins are used. A0, A1 from the microprocessor line goes to these two pins of 8255. When these two are 0, port A is selected. And if the CS pin, you are having the MSB bit enabling 8255, then the address will be 80. Similarly, port 01 will enable port B and the address will be 81H. And 10, port C will be enabled, the address will be 82H, assuming the MSB bit is 1. So 82H. Control register 11. So 83. So the 8 is decided by the MSB bit, which is connected for enabling 8255, and 0, 1, 2, 3 change as per the address A0, A1, 00011011. See this. This is the what you call as the control word format. D0, D1, D2, D3, D4, D5, D6, D7. Here the most significant bit D7 is if it is 1, it refers to IO mode. If it is 0, it refers to BSR mode. And D5, D6 bits, if they are used for mode selection. If it is 0, 0, if port A becomes mode 0. The 0, 0 mode, mode 0, which is nothing but simple IO operation. If this is 0 and 1, mode 1 is selected. That means interrupt-driven IO. Port A can be either in simple IO or interrupt-driven IO or bidirectional. 1-0 mode will be bidirectional. So port A has the facility to become simple IO, interrupt-driven IO, or bidirectional. And D4 is for port A. If I put 1 in this bit, it is input port. If I put 0 in this bit, port A becomes output port. And D3 is for port C upper. Port C upper and port C lower can be separately defined as input ports or output ports or all input or output ports. So therefore, we have got another advantage here. D3 is for port C upper. If I put 1 here, it is input port. If I put 0, it acts as an output port. D2 is for mode selection of port B. Port B can be mode select. If it is 0, it is mode 0. And if I put a 1 there, it is interrupt-driven IO. Port B does not support bidirectional. Therefore, only single bit is given here and 2 operations selections are available for port B. D1 is for port B. If I put 1 there, it is input port. Port B is acting as an input port. It can be defined as input port. Or if I put 0, it can be defined as output port. And this is for port C lower. Port C lower. Now you see, you take an example, generating control word for simple IO. For example, we want to input a byte through port A and output the byte through port B. So input through port A, output through port B, and input 4 bits through port C lower and output the 4 bits through port C upper. So we use PA0 to PA7 for inputting the data. We output the data through PB0 to PB7. These pins are connected to the output device. Here, these pins are connected to the input device. So the input device, whatever the data it gives, it is connected, it is through PA0 to PA7, it comes through 8255 and goes to the accumulator. Similarly, whatever is in the accumulator goes through 8255 and through port B, PCB0, PCB7 connected to the output device. So that way, input device is connected through port A, through 8255 to the microcontroller, to the accumulator, and from the accumulator through 8255, it goes to port B. Similarly, here, CL, 4 binary bits, lower bits are acting as input port, and upper nibble of port C acts as an output port. So for that, what we do? See that D7, simple IO, I put 1. D6 and D5, 0, 0, because we say that port A is simple IO. D4, port A is input port, so 1. D3, it is port C upper, port C lower. Port C lower input. So this must be port B upper. Port C upper, we put 0, output port CU, and D2 is for port B mode select. simple IO, so we put 0. D1 port B is output port, so 0. D0 port C lower is input, so 1. So after putting the command word with all these bits position depending on the command word assignment, we get 1001 1001 gives you 9, 0001 gives you 1. So command word 91H. This command word 91H has to be loaded into the command register CR. So move A 91H. See that? Very simple. IO operations deal only with these two. Accumulate, move the data to the accumulator and either input or output, give the port address. So move A91H. Where do you want to place it? CR. So the address of the command register is 83. So move A91H, out 83H. So now the 8255 is programmed. It is for simple IO operations with port A as input, port B is output, and port CL as input and port C upper as output. So this is how very easily we have programmed it, and we can reprogram. We can use the port A as output port, port B as input port also by changing the assignment pins here. So now for this operation, we have done 83, move A91H, out 83H. Here, next we want to input through port A in 80H. 80H is the address for port A, and you say out, it has gone to the accumulator, and from the accumulator you say out 81H, address for port B. So what you have input through port A will be output through port B, which is 81. Then port C lower is tricky because we are inputting through the lower 4 bits and outputting through the upper 4 bits. So in 82, address for port C lower and port C upper is the same as for port C. So address for port C is 82H. So we say in 82H. After that, we shift left, swap the nibbles, lower nibble to the upper nibble. So that's why I gave you the technique RLC, 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 RLC. When I perform 4 times, automatically the lower nibble, the information received in the PC lower will be shifted to PC upper points. And when I say out 82 from the accumulator, it goes to port C again. That is through ports upper, port C upper, it is transferred. So this is how we accomplish very easy. Blinking of LED is for square wave generation. So this very, very interesting. What is blinking? To make a particular bit high for some time, retain it for some time, and then lower it, make it 0, and retain it for some time. So it will be in a high position for some time and low position for some time. Therefore, we will say I means 5 volts, low 0 volts. It will be output will be changing voltage from 5 volts to 0 volts, producing a square wave. So when I put one LED, if it is connected, will burn. If LED, if I put 0, then the LED will go off. So when the 5 volt is supplied, LED goes on and it is retained for some time. And then when it is at the end of the time delay, the content is reduced to 0 and the output will become 0. The LED also will go off. So burning and not burning will give you a blinking operation. Now condition is how to make the LSB of port A. See, you have got port A, port B, port C. Port A, port B, port C are decided by the addresses. See, these are the addresses. And now we say LSB of port A. And here I have the option of again redesigning, saying that port A, port B, port C, all 3 ports are configured as output ports, so that you can switch from port A, 80, you can go to 81, and all the changes you can make place. So here we see all the 3 ports, PA, PB, PC, can be configured as output ports. In that case, the command word comes to 80H. So this 80H has to be moved into the command register. Command word MBIA 80H is output to 83 command register. So
gratitude opens the door to the palm, the wisdom.
Okay, MBIA 80H, out 83. So we are saying that the for 8255 is programmed for all 3 ports, output ports. Now our point is to make LSB bit of port A blink. To make the LSB bit means I must make it high. So LED on code, we have got on code and off code. You load the code and output it. That's all. Call a time delay and come back after the time delay. You load the off code and output it and call a time delay. And after the end of the time delay, you repeat the whole process. So that is the algorithm for this. So LSB bit is now 1. The code is 0, 1. The off code is 00H. So similarly for MSB bit, the code is 80 because the LSB bit, MSB bit here 1 is going there. So 80H. And of course, the off code is 0. And for both LSB and MSB, suppose you want both the LEDs to be blinking, MSB bit 1 and LSB bit 1, the code is 81. See, I am changing the code. I am designing the code 01, 80, 81, and all the 4 nibble, lower nibble, 0F, upper nibble, F0. So like that, you can set the on code and the off code, and you can also select port A, port B, or port C. In this case, I have selected port A, and in this, I am saying that LSB bit port A to be blinking. For that, this program is written. MBIA 80H is the code for BSR, what is the command register code, and it has to be placed in the command register. So MBIA 80, out 83. Then comes load the on code, MBIA 01H and out 80H. So PA out 80H means port address gets 01H, port A gets 01H, the LSB bit, if there is a LED, it will burn. If it's connected to a CRO, it will go up. So it will, and then you call a time delay, 1 second time delay, and retain it so that the LED remains burning. And then at the end of the time delay, you have to send the off code MBIA 00H and send it to out 80H. Port A address is 80H. If I want port B, change it to 81H. So that's all. Port C 82H. Call 1 second time delay, and at the end of the time delay, again you come back. So you start doing the same thing. Then you see that the LSB bit of port A will be burning and going off, blinking, or it will be executing a square wave. So this is about I/O. Then I have also done it, just bear with me for 5 more minutes. BSR mode. It is a bit set reset mode. It will affect only the command register, port C. For that, the format is different. So you see, you have to have 0 in the D7 position. It is a must because I/O is 1, and for BSR mode, D7 position must be 0. And then you have what you call the D0, set or reset. If you want to set the bit 1, reset the bit 0. So that way you can put. And which bit? That is the question. See, that is selection is there. So we use S0, D1 bit, D2 bit, and D3 bit for selection. S0, S1, S2 selection bits. If they are 0, it will select the I told you only a port C is affected. So PC0 will be selected. So once the PC0 is selected, depending on whether the reset bit is 1, it will be set or it will be reset. So PC0, the set code is 01 and the reset code for PC0 is 00. Say on and off code. Similarly, if you want to set PC1, you see you select PC1. Remaining things must be 0. We'll put everything 0. This is a important 0 because it is BSR mode. And when I come here, I want PC1, so 001, set code 1, then the value will be, X code will be 03, or the off code will be 02. If I put 0 here, 02. So like that, you have the select operation, 111 will select the PC7. If you want to have on code, put a 1 here, that will give you 0F. And if you want the off code for the PC7, the 7th bit of PC, it will put 0 here. So O0E, 0F or 0E, 1 less than the set code. 1 less than the set code will be the off code. You see the 030 to 05 like that. 22 plus will be your on code. See 1357. So this is how it says we can get that what is called PSR of mode code. So to blink LSB of port C, now we cannot have any option A or B, only port C. We want to blink BC0. So PC0 to blink, we know the on code is 01H and the off code is 00H. Okay, to blink the PC1, 03H and 00H. Yeah, the code is different, which from you have to take it from the table. So to blink the LSB of port C, all the 3 ports, PA, PB, PC, this is a must. You must know, even though you are having BSR mode of operation, the IO mode of initialization of 8255 is a must. So what we say, we make port A, port B, port C again, all of them to be output ports, so that the command word is 80H, I send it to 83H. So MBA 80H, out 83H. So that way you see that we have initialized 8255 for this all ports to be output ports. Now we are setting the BSR code for PCO to be high. So for PCO on code is 01 and out 83. The address is not to port C, it has to be addressed to command register. You are going to redefine command register as many times as possible in PSR mode, but this will not affect anyway these IO settings. That is very, very important. You should know that it is a necessity that you do IO initialization. After that, you can, any number of times, because you know the MSB bit is 0, it is not going to alter these settings here. And now for everything, we are going to say MVA 01, out 83H, call time delay. You are going to retain it for some time. And then you want to have LED off. So set the off code for PC0, which is 0, MVA 00H, and send it to command register. See, every time you are sending to command register, call time delay, then jump start. So here you see we are changing the on code and the off code for the different bits, but we are sending the information only to the command registers. So LED on off starts blinking different bits as given in the table. Send code to command register 83 only. So this is the assignment I have come to. See, you have been listening to all these lectures on programming and programming techniques, addressing modes, and the instruction set. I did not take it like that because in a rush up session like this, I cannot do individual instruction set explanation. So I use the instruction and I selected about 17 techniques to bring different important instructions to your knowledge. So that way we have done that. Then we have seen how IO can be interfaced. So we have done all that. And now we can write ring counter using IO operation, shift counter using IO operation, modulus counter using IO operation. These are all. Ring counter means the LSB bit will be 1, remaining things will be 0. After that, the LSB bit will come to the second LSB. So 1 will be shifted through left every time. Only one will be shifted along the accumulator. So that you should know how to write a program for it. And shift counter means for you shift 1 into the LSB bit, and next time 2 ones will be there, next 3 ones, because as long as the MSB bit is 0, ones will be shifted into the LSB bit side. So you see that first time 1 bit, second time 2 ones, and like that 8 ones will become 1. When the MSB bit becomes 1, 0 will be started, introduced in the LSB section. So 1 0, 2 0, like that 8 0, so that you get mod 8 operation, mod 16 operation. Ring counter will give you mod 8 operation. Shift counter will give mod 16 operation. Then modulus counter, you can have mod 5, mod 6, mod 7, mod 3. All that also, you know, we can write. Employing IO mode, byte operation, simple. Simply try the same thing with BSR mode, bit operation also. So this is a kind of assignment I'm giving it to you. You try and you can respond to me. If you need any help, We will send the solutions to the staff member, madam, or you can also write to us directly. Okay, thank you. So these are the embedded projects, sensor-based embedded microcontroller projects, which we can do it in our, I have no time, and tomorrow I will discuss about all these projects, which you can do. You can join internship training in Floronics and enjoy Atmega 328, because that is the chip we have selected. You may say, why Atmega 328, sir? It is an embedded microcontroller. Yes, wait and see. Tomorrow we'll have a nice discussion. See you tomorrow. Thank you, sister. Sorry.
Thank you. Thank you, sir.
I have transferred all my
Knowledge.
information, knowledge.
Information.
Okay, fine. I hope God blesses my
Yes, sir.
presentation and it will be useful.
Thank you, sir. It was very nice, sir.
So we can assemble again at 2:30.
Yes, sir.
I will straight away start with small introduction. And
yes, sir. Sure, one short vote of thanks, sir.
Yes, sir. Thank you.
Yes, yes. Madhumita?
Yes, sister. Thank you, sir, for enlightening us with your knowledge. Learn from yesterday, live for today, hope for tomorrow. The important thing is not to stop questioning. Now the session is open for clarification.
Yes.
You can post your questions in chat box too.
Yes. Or my email. I will.
Yeah, I think we can also ask through email if they have any doubts.
You can, because
once
I
they
can
start doing the assignment, they will have some doubts, sir. Yeah.
Yes, sir. This is now they have heard it. It's very difficult.
Yes.
But for MSc student, they might have been listening last year itself.
Yes.
They can reach to my expectation. Papa, let us see. I have given them assignment. If they can do it, very good. Otherwise, I will help them through email correspondence. And they are most welcome to call me also, or they can come through you also. I will be willing to help you. So thank you, sister. We'll meet again at 2:30 tomorrow.
Sir, just a minute, sir. Madhumita, just call Rachel.
Yes, sister.
Yes.
No duty is more urgent than that of returning thanks. Thanksgiving is a time of togetherness and gratitude. I now invite Ms. Megra of 3rd BSc Physics to express our gratitude through vote of thanks.
Gratitude opens the door to the power, the wisdom, the creativity of the universe. I deem it a great honor and privilege to render the vote of thanks. First and foremost, I thank our God Almighty for making this meeting a resounding success. I sincerely thank our chief guest, Dr. G. Kumar Satyan, for sparing us his precious time amidst his busiest schedule to enlighten us on 8085 microprocessor addressing modes and programming techniques. I would also love to render my sincere thanks to our secretary, Reverend Sister Flora Mary, our principal, Dr. Reverend Sister A.S. De Lucia Rose, our vice principal, Dr. Reverend Sister Kulandai Thrace, director of SSE, Sister Josephine Jairani, and our HOD, Dr. Reverend Sister Jessie Fernando. I extend my heartfelt thanks to our faculty for their tireless effort in making the gathering a great success. Last but not least, I thank my beloved friends for their keen and patient listening. Thank you, one and all.
Thank you, Megra, for your kind words of gratitude. The only source of knowledge is experience. Today, we have gained the knowledge through this wonderful experience. Once again, I thank you all for your active cooperation throughout this webinar. Thank you.
So thank you very much. Some of you have been till the end. I really appreciate your patience, and it was a wonderful talk. So we shall meet tomorrow again at 2:30.
Yes.
So this will be only 2 days program, so I expect all of you to be on time. So thank you very much.
Thank you, sister.
Thank you, sir.
Thank you.
We'll meet tomorrow, sir. Have a good day,
tomorrow.
Sir. Yeah.
Again, same time, 2:15, I will be there. 2:30 we'll start the lecture.
2:30 sharp we will start, sir. Straight we'll start with your talk, sir. Yes, sir.
Yes, thank you.
Thank you, sir.